Cuando estemos en silencio. Me digas, vamos a streaming ya. Vale. Okay. Hello, good morning to everybody, and welcome to the Directors Colloquium of the IAA. I think this week has been a very important week for astronomy, no doubt. In less than 2 years, we have got 2 fantastic results. The first one was, of course, the discovery of the gravitational waves. The second one is the one that has been presented this Wednesday in different places of the world, in which we have shown for the first time the image of the shadow of a black hole. I think it's fantastic because both results are consistent in general terms with the theory of the general relativity. We are very proud here in the Institute, since we have been taking part in this experiment, in the well-known already as the Event Horizon Telescope, the telescope that is able to reach the limits of the event horizon of a black hole. In fact, we have today a great speaker, yes, the best speaker we can have in order to understand well the results of this experiment. Our colleague, José Luis Gómez, has played a leading role in this experiment, and he is going to explain, as mentioned, all the details, all the main details related to the experiment. All those that are here already know José Luis, but let me introduce for those that are seeing this streaming event from outside. José Luis was a PhD student here at the IAA, working in the physics of the relativistic jets. I am sure that at that time, when he was a student, he was already thinking that the best news he could have along his scientific career was just the first image of a black hole. It was a dream that has become reality now. After being here a PhD student, he went to US. He was working at the Boston University, where he had a very fruitful collaborations there. He was for some years. And later he came back to the Institute, where he is just now investigador científico. He's leading here the research of the physics of the relativistic jets and playing a relevant role in collaborations like the GMBA, the Global Millimeter VLBI Array, the observations with the satellite antenna radio astronaut. In fact, he has got up to now the image with the highest angular resolution obtained already in astrophysics, 14 microarcseconds. It's no doubt one of the leading players in this high resolution angular astronomy world of astronomy. Okay, before we go into the talk, that's what you really want to do, just let me show you just this image here, in which you can see the cover pages of many different newspapers around the world. It has been really I think that on Thursday, I would say that all the most important newspapers of the world have in their front pages just the image of the black hole. You can see there the New York Times, the Guardian, the Le Figaro, La República, and of course all the main Spanish newspapers, El País, El Mundo, La Razón, etc. The newspapers from Mexico, newspapers of course from Granada, from many places of the world. It is without any doubt a very good indicator of the impact that this news has had in astronomy. Okay, José Luis, now we are really looking forward to listening to you.
Thank you, John. That was a very nice introduction, so I thank you very much, and I thank you all for being here. And I will try to give you an overview of what has been 2 years of very, very hard work by more than 200 people. We published on Wednesday 6 papers, some adding about to 250 pages. So I'm going to try to summarize all this work in just 45 minutes. So forgive me if I prepared the presentation just in a rush. You could imagine how it has been for these past days. So it's been really, really crazy. And let me just start with the image that I think you all have seen now. This is the first image of a black hole, and it was taken in the center for the center black hole in the radio galaxy M87. So this has been everywhere, and Shep Dolleman just sent me yesterday this very nice picture. You can see here Shep, and you can see here Maciek. Apparently he got a glimpse of what is inside the Event Horizon telescope, and the Event Horizon of M87. And so this has been really in all media. And I think you all know Katie Bowman by now. This is a picture of her, and I've been also asked many times during these past days what I felt when I saw the image. And I think this is a very powerful image that summarizes what we all felt when we saw it for the first time. You can see Katie here. She just can't believe what we have just got. And she has been really, really famous. She has been in, trending topic in Twitter. And I think some of you may wonder what happened with this. I mean, she really deserves all this attention. She has been compared with MIT computer scientists that help the programming for the Apollo mission, and she has done really an amazing job. She really deserves this. I'm really proud to see her here. I mean, she helped to develop one of the EHT imaging library that we used to recover the image. She created a synthetic data set. She did some of the imaging challenges, and she is one of the coordinators of the paper for which is the main paper with all the imaging and all the analysis we did. And I was really honored to be part of this really, truly amazing team. You cannot believe how these people work. It is really amazing. So I just want to say, felicidades, Katie, you really deserve this. And this is, by the way, the first time we saw, and I will talk about this a bit later, that we did have coherent images of M87, and she was presenting this, and we were all really happy to see that. So, but this has been not only an effort by someone like Katie, so this has been truly a really international effort of really amazing people. And you can see here Kazu Akiyama, you can see here Sarah Isasun, you can see here Katie, of course, Michael, you can see Monica, you can see Maciek, you can see Ferial, you can see Sarah, Ivan Martinidad, our colleague here in Spain, Thomas Kirchbaum, Elia Madeiros, Andrew Child, Svelana, and of course, our director, Shep Doleman, who really, this was really his dream. And I really would like to have a big round of applause for 200 people that made this possible. We were really a team. Not just a person, a real team. And this was one of the most beautiful experiences. So, why did we take the image? M87 is in the constellation of Virgo. It's known in radio as Virgo A. And with the EHT, we have been zooming into with an astonishing angular resolution of just 20 microarcseconds. So you can see here when we are zooming into M87, this was actually the first known jet, the first known extragalactic jet. It was discovered by Curtis in 1918. And you can see we have been zooming into the jet all the way to obtain the final image. This is what really lies within 8 years. This is the main power, the main engine that powers all AGNs. It's a huge 6 billion solar masses black hole. And how did we manage to take a picture of a black hole if they are absolutely black? So M87 is surrounded by a accretion disk, and this produces, of course, a lot of photons, which is what we see as AGN. And you can see that the path of the photons are determined by the gravity of the black hole. When they are really close, they are bent, and when they are really too close, they just get into the black hole and they are absorbed. They cross the event horizon. When seen from Earth, what you see here is the combination of the two effects to produce what we call the shadow of the black hole. This is a completely dark central region surrounded and silhouetted by the emitting plasma around the black hole. And this is what we have seen. How is this produced? This was actually, as you know, first studied by Schwarzschild and then Kerr, and I'd like to introduce you to the actual first simulation of a black hole. That was obtained 40 years. And this is the image that Jean-Pierre Luminet calculated of what should be the shadow of the black hole. By the way, I forgot to add here, to quote him, because he actually mentioned 40 years ago, he did, I mean, if you go to the paper, he actually mentioned that one of the best places to see this was M87. This is truly amazing. When we saw that, we were like shocked, like, I mean, this cannot be true. He actually mentioned that 4 years ago. So what you have here is what is the path of the photons around the gravitational potential of the central black hole, and you can see here that the photon capture orbit is determined for a Schwarzschild black hole is given just by this simple formula, square root 27, and the gravitational radius, which is, as you know, just a function of the mass of the black hole, and it's about half of the Schwarzschild radius. So if you are able to determine what is the size of the black hole shadow, you can get actually what is the size of the mass of the black hole if you know what is the distance. So this has been, I will see later on, this is just one of the key equations that we have used to prove that we are seeing a black hole. The image is quite easy to understand. So you have this warping of the space-time near the black hole. So you are seeing the image actually from the photons from behind you, and you see the upper side of the accretion disk, and you can actually also see the back part of the accretion disk on the bottom. Very similar to what Luminet did. And this is 40 years later, and I will talk about this a little bit in more detail later on. I'm afraid the projector is not as good as it was in Madrid, but this is a simulation that we have been doing by the EHT collaboration of what is the expected situation when you have a supermassive black hole surrounded by this accretion disk. So let me move forward. How did we do this? How did we manage to get 20 microarcseconds? For this, we used an array. For M87, we used 7 antennas. IRAM here in Picoboleta play really a key role, and we also have ALMA antennas in Mexico and in Hawaii. So these were all the different dishes that South Pole also for the southern sources that played a role in the observations that we just presented a couple of days ago. So this is the global array that we used. You can see here the dishes that we used in 2017. You can see here ALMA, we used an equivalent size dish of about 70 meters from ALMA. The second largest is LMT together with Picoboleta. These are the most sensitive antennas, and we are observing almost every year. And for 2018, we also observed and we included GLT. NOEMA is going to participate in 2020, and as well as Kitt Peak. So we are expanding our array. These are our two main targets. The EHT was developed with a single aim of imaging the black hole shadow. This was the whole purpose of the EHT, which was designed 10 years ago. And we had in mind two clear targets. We had the center of a galaxy, say, with a black hole mass of about 40 microarcseconds. And you can see here that the expected shadow diameter is about 40 to 50 microarcseconds. So it is actually the largest. And we had also M87. For M87, we had not a clear picture of the mass, because there are two different measurements of the mass, from the gas motion and from the star motion. So we had this range of possible masses for the black hole, and we know the distance also pretty well, and we expected to have a black hole shadow of the order 20 to 40 microarcseconds. So we were not sure, because our angular resolution is about 20 microarcseconds. So we were not sure if we could actually take a picture of the black hole shadow in M87. But nevertheless, we tried. And for this, we had to really, and this was a really sharp effort, we had to really improve the VLBI as we know it. This is the recording rate increasing with time, and you can see here that we have reached, for 2017, 32 gigabits per second. This is more than one order of magnitude of regular VLBI. This has been a huge effort. And with this, we are achieving these sensitivities for baseline detection, which is even smaller than centimeter VLBI that we regularly use and we have used for the past decades. And by the way, this is This is a picobeleta. Miguel knows this very well. This is the recording system. All the hard drives. We are recording more than 2 petabytes of data, and with this observation, this is the picture from picobeleta. And one of the antennas that was really instrumental for getting this was ALMA, using phase ALMA. It took us more than 3 years to develop the phasing of ALMA, and this is just an example of how important is ALMA. These are the fringe detections without ALMA. You can see here that it's quite difficult to distinguish, to determine what is the fringe between 2 different baselines. And this is when we add ALMA. ALMA provides the determination of what are the clock offsets and the phases differences between ALMA and the rest of the antenna. So we use this to calibrate each antenna, and this allows us to determine the fringes between 2 different antennas in which ALMA is not participating. So ALMA is really instrumental for this, increasing the signal to noise. And these are the observations. You have seen one image. I know I could not stress this more, and I was really picking with this in the main paper, in paper 1. We need to show that we got 4 different experiments showing exactly the same image. This is not just a chance. This is not an image that we obtained because we were lucky. We did 4 different observations in April 5, 6, 10th, and 11th. And this is the UV coverage that we were getting. This corresponds to April 11, but you can see here April 5, 6, 10, and 11, and you can see here how the rotation of the Earth allows us to fill the UV coverage. This will be the equivalent dish of the observation of the synthesized antenna, and you can see here the Earth rotation, the aperture synthesis allow us to fill the gaps in the UV coverage, and this is the actual data we obtained. This was the 2 years, and it took us 1 year for correlation and data analysis, which is what I'm going to comment in the next few slides. These are the signal to noise ratio for this detection. This is 1 millimeter, 1.3 millimeter. These are signal to noise of the order of 1,100. This is even larger than centimeter VLBI. This was amazing. It really, truly amazing. I remember going to MIT in Haystack, and Shep was thrilled because we were seeing fringes with a signal to noise of 1,000. We started to think that this was going to be the experiment. By the way, we had to be really lucky because we were observing 7 different geographical locations, actually 5 different geographical locations, and we were extremely lucky with the weather. It was like Superman blowing all the clouds and everything. It was really, truly amazing. The data is unbelievable. 2018 was not that good by far. Anyway, so these are just samples of the closer quantities. I'm not going to get into detail about the closer quantities, but these are just to give you an idea of the quality of the data. These are the thermal noise that we are expecting from what we call trivial closures. You can see here that the thermal error and systematic errors are really small. You can see here now the persistent structure between these baselines, ALMA, LMT, SMT, showing this clear structure, the persistent structure, and even some hints of variability between the beginning of the experiments and the ending of the experiment. So indication of source evolution that we are still analyzing. This is another example of the amazing quality of the data. And we were not, we didn't want to just use one pipeline. We correlated the data in 2 different places. Correlation took us more than 3 months in supercomputers, and we did that in both in Bonn, in Germany, and we also did that in MIT, in Haystack. And these are, we use also 3 different pipelines for data reduction. We use HOPES, which is developed by Haystack, CASA, and regular APES. And you can see here the plots of the different quantities, and you can see here what are the closer quantities for the amplitude, for the phases, and the trivial closures, and for phases and amplitudes. And this is truly amazing. The systematic error in amplitude is 2%. To give you an idea, this is of the order of just the typical of CASA when you use, of ALMA. And these are very long baseline interferometer. We have never seen this in past VLBI observation, even a centimeter wavelength. 2% amplitude, 1 degree in phase. This is truly an amazing set of data. And And we had to make an image, and I cannot help but to show this beautiful movie made by Daniel with data that we provided to him. And you can see here, this was shown in Shep's presentation in Washington. You can see here how we reconstructed the image. You can see that the filling of the gaps in the UV coverage allowed us to recover the ring in M87. And how do we get an image? How do we go from this, which is the equivalent telescope? This is the actual data. These are the visibilities. How do we get to an image? All the reports were short, like, you don't get an image. I mean, what you have been talking about reconstruction? I mean, this is not. This is just a supposition, a simulation. No, this is an actual image. You only have to take a Fourier transform of the visibilities to get an image. And I'm going to show you just an example of one of the algorithms that we use, which is CLEAN. And you can see here, this is a deconvolution of the image, and you can see here how we are recovering the image by deconvolution of the visibilities to produce the image that we have obtained. And this is just an example of CLEAN. I'm afraid the projector is really not good to show you all the fine details in the image. But as we did for the calibration of the data, we didn't want to use just a single script for deconvolution. We also used two different imaging scripts, HT imaging and Smiley. These are different type of scripts. CLEAN has been always used in imaging reconstruction in VLBI. So if you use CASA, if you use APES, this is what you regularly use for deconvolution of your images. This is what is called forward modeling, forward deconvolution. And we also use these two, EHT and Smiley, developed mainly by Harvard, and Harvard in collaboration with Asia. And these are using regularized maximum likelihood methods, such as maximum entropy method, which can provide you even with some super resolution, some resolution even better than what you would expect from the theoretical diffraction limit. And you can see here the images are even with this higher resolution, and the three of them showing exactly the same structure. The final images that you have seen around the world has been obtained by combining all these different pipelines. We actually used a beam which is more similar to the regular CLEAN. So just to be on the very, very safe side. And let me just go a little bit, I explained the data, how we correlate the data. Let me show you how we did the image, and this is a very nice story. So this was the first picture. We saw the visibility, so we thought, this is going to be it. And we want to be really sure that nobody can tell us that this may be fishy. So, and when you have such a small UV coverage, you may be biased. You may be, if you see an image from a colleague who is a very respected colleague in the field that has done thousands of images, and you see that, you may get biased, and you may try to get a similar image with your reconstruction. So to avoid this, we made 4 different teams. They were mainly focused on the different algorithms, team 1, EHT imaging, team 2, Smiley, team 3, CLEAN, and team 4, CLEAN, different regions, it's in basically Americans, global, and this was cross-Atlantic, basically East Asia. And we were completely independently. We were not even sharing emails. We would meet in a meeting, and we would not talk to each other about the data at all. It was really quite funny. We could not speak about this. And this was going on for 2 months. So we were doing our own images, and within our own team, we were discussing within our team, but not with the other one, making our final images. And then we had a meeting in Boston, the Black Hole Initiative in Boston. And this was the first 4 images that we obtained. And let me go you a little bit more about the story, because this is quite nice. What we did was we met, as I said before, in July 23rd in Black Hole Initiative. And the first thing we did was to compare the images just with using a cross correlation. So we wouldn't even see each other images. We just gave it to a computer and asked the computer, do they look alike? Only after we got a positive answer, we proceed further. And that was a positive answer. This is when Katie, the previous image that I showed you, Katie did the cross correlation, Katie did the analysis, and Katie said the cross correlation of the 4 different teams' images are higher than 95%. And then we were all thrilled. And this is the moment that we captured when we were seeing that we had a consistent image. Of course, we were having reporters all the time. And this was the day after that when we actually shared the image. And that was the first time that we thought that we really imaged the black hole shadow. And that was July 24, and you can see all the happy faces, especially Shep, and the final image of the black hole. Of course, after this, there were many celebrations, and we went drinking, and more drinking, and singing, and the reporters, and the champagne, and everything. That was the moment. So it's been 9 months of a hell. 9 months knowing this and not telling everyone. 9. So there I gave birth 2 days ago. So literally, that was truly amazing. Anyway, we were not happy just using 14s. We were not happy using this blind imaging. We really wanted to make sure that we can recover truth images. So Katie did this. Katie simulated data. These are simulated images of a ring with a symmetric structure, a crescent in which one side of the ring is brighter than the other, a disk, and a double source. And we produce synthetic data sets. We produce the data that we would have got with the EHT from these images. And from this, we took into account exactly the same imaging, the performance of the different dishes, the weather condition, the gains of the different antennas, the UV coverage, absolutely the same thing. And this is the data. If you remember the other data, it was very similar to this, the actual data. On purpose, we simulated data with one of these null, which is the characteristic null that you would expect from a crescent. So we generated this, and we gave this to our pipelines. And we knew the answer. So with this, we knew what we should get. And we had to fine-tune our parameters. We had to play with this to try to recover the actual image. And this is so we did a survey parameter, and these are the images obtained from this map, from the ring, the crescent, the disk, the double, and our GRMHD simulation. These are EHT images, and these are smiley images. And you can see with our pipelines, we were able to recover the precise structure, even the crescent with the asymmetric ring structure. So we did this parameter search exploring with diffmap. We ran more than 1,000 images with diffmap. To give you an idea, to make one single image, it could take you 1 day. So we had to produce this script, and I was very lucky that in our team we managed to get one of these scripts for diffmap, which has not been, it was not available, and it was really necessary to do this parameter search. 37,000 images with EHT library and about 10,000 with Smiley. So we made 50,000 images of the data. This is why it took us 2 years to analyze the data and publish the data. We did 50,000 images, and we found for each one of the pipelines what are the best parameters that would reproduce the ground truth images. And only after we knew we could use these parameters to recover the ground truth images, we used them to image the actual data from M87. And this is what we got. These are the final images using this set of parameters, and these are for April 5, 6, 10, and 11, and these are diffmap images, these are EHT images, and these are smiley images. You can see the similarities among the three of them. And for the final fiducial images, what we did was to blur the EHT imaging and the smiley images with a similar beam as we obtained with diffmap. And these are the three images blurred with the same beam of the same data set, and you can see that the similarities are really striking, quite remarkable. And these are the final images. This is the one I'm going to put in as a poster in my office. These are the 4 different images, and I could not stress it more. We did exactly the same very rigorous analysis, 250 pages of analysis of this data set, and we did it for 4 different, completely independent experiments. You have seen one image, but I cannot stress this more. These are 4 different experiments. And the 4 of them showed this very same structure of the asymmetric ring structure in M87. So we were not lucky with just this. Of course, we wanted to have a theoretical interpretation, and I was expecting this view graph a bit later on, but anyway, since it is here, I will comment it. So I'm going to explain now a little bit about the theoretical interpretation. As I mentioned before, this is one simulation. This is not just something you run in your laptop. This is a absolutely full GR-MHD simulations. These are running on supercomputers. It takes months to produce each one of these. I'm going to discuss a little bit how many of these we produce. But if you go to the presentation in Washington, you could see Avery Broderick explaining with a beautiful plot of all the different simulations that we did. So these are the simulation, and we did a similar process. We used EHT library to determine what would be the data that we will get from that. So we will get, as we did with the synthetic data, we produced synthetic data set. And we just and we image with the same pipelines and the same parameters that we use for M87. So we converted this in data, we use the very same imaging script. This is not just a convolution of this. This is an image obtained from the imaging pipelines. And these are the image that we would expect if this is actually what is going on in M87. So this is the reality. And this is what we would expect with the actual capabilities of the EHT in the 2017 campaign. And this is the actual image. So it is really quite striking. They are so similar that we were really truly amazed. How did we do that? So for the GR-MHD simulations, we have run 43 GR-MHD numerical simulations. This is the largest set ever done of GR-MHD simulation of a black hole, a supermassive black hole. We use different codes. We use a 3D simulation from BHAG, AHARM, Coral, HRM. So 4 different codes. We had 2 different types of accretions. If you are familiar with accretions of the supermassive black hole, we had 2 models. We had the same and the MAD models. The same are for the standard normal evolution, so not high magnetization, and this is for magnetically arrested disk, in which the magnetization is significantly higher. And we played with the black hole spin parameters, and these are for the same parameters, the spins that we use, and for the MAT model, the different spin parameters for the black hole. And with this, we produced 60,000 images. There are 60,000 images using this numerical simulation. And for this, we use also 3 different ray tracing codes, IPOL, Raptor, and BHOS. And we use different inclination angles with values similar as we expect for M87, which is around 18 degrees. And this is the question that I got in Madrid, the thermal electron, the really good question. And this is probably the most important parameter that is within our simulations, because we don't know what is going on in there. We don't know how, in these situations, in high plasma beta, we really don't know how the ions and the electrons are coupled. So we had to parameterize this, and we use this parameterization, which is just a function of demagnetization. So we will have colder electrons with high plasma beta in the disk, and warmer, low beta plasma, so high magnetization in the jet. And so we did the simulations, and you see here, these are, for instance, the results from SANE. This, by the way, corresponds to paper 5. And you can see here, this is black hole spin. And you can see here the different spin values and the different values for R high, so for the magnetization, the plasma coupling. You can see here the different images. You can see here the lens ring, and the emission from the accretion, and these are the MAT magnetically arrested simulations, again playing with the different spin. And you can see here, this is the lens, the ring, and the horizon is here, and you can see that the orientation, the side of the ring that is brighter depends, of course, of the spin. These are just a plot showing from where the millimeter photons that we are capturing with the EHT are coming from, and this is for low R high and high values, and these are for the MAT values with this spin parameter, and this is the ISCO, this is the observer, and you can see that with MAT magnetically arrested disk, most of the emission come from the ISCO. In the case of the same model, situation is different. With high magnetization, we get most of the emission from the jet, and with low magnetization, we get emission basically from the ISCO. And how did we use the fact that the one side of the ring is brighter than the other to determine what is the actual direction of the spin of the black hole. And you can see here, the cartoon that you can see in paper 5, you can see the sense of rotation of the accretion disk of the jet and the black hole spin, and you can see that only in the cases in which the spin of the black hole is pointing away from us, you could actually reproduce that the brighter side of the ring is in the south. So we know that the disk in M87 is rotating clockwise. And so we had to do also the fitting of the simulations to the actual data, so to find what are the good models. So these are, for instance, a particular GRMHD simulation. You can see here, this is the unconvolved, unblurred emission. This is the convolved emission, and this is the fitting that we do to the actual visibility. So we use this data. We feed the data to the actual visibilities, not to the images, to the actual data to find what are the good models. And for this, we obtain what is the distribution on the M/D. So if you remember, this is the key parameter. This is what we really want to measure, which is what will give us what is the mass of the black hole, of the expected black hole. And you can see here the fitting is around 3.8. These are for different types of Markov chain for Monte Carlo fitting. We use Themis and Gina. I'm going to explain a little bit more about this. But you can see that the distribution peaks with an M/D of about 0.36 microarcseconds. And this is the width of about half of microarcsecond. So this is the key parameter. This is what we really want to know, because you have this image, but you have to determine what is the actual mass of the black hole. And as I'm going to show you in a minute, to check if this is consistent with the previous measurements that we had. And so we did this also for the different set of simulations. These are MAD and SANE simulations, different values of the magnetization, and we used these fitting algorithms to determine what is the value of M/D. And then we have to establish a scoring of the imaging to determine which one of these many different models that we produce actually feed the data. So for this, we compare the data to our average model, each particular model to the average model, and we use this algorithm for this. This rejects us some particular models. For instance, this MAD model with a counter-rotating accretion disk is too variable, so we discarded this. So we know this is not the case of M87. And we also used to set other constraints to determine which one of the GRMHD models we have computed agrees better with the data. We use this consideration, the relative equilibrium, the production of X-rays, and also this proved to be one of the main constraining for selecting our GRMHD models, the jet power that we will get. And this rule out, as I think I have in the next slide, yes, this rule out all the Schwarzschild black holes. Any non-rotating black hole would not be able to produce the jet power that we have seen for decades, actually for more than a century now in M87. Let me now go you to the paper 6, and this is where we did the fitting of the data in different ways. We did fitting to the actual visibilities and fitting to the images, and these are, as you saw here, the UV coverage. This is the visibility data we obtained, and so we fitted a different crescent model, crescent and a regular crescent, a crescent with an extra Gaussian, and also GRMHD models. Why did we do this? Why did we do this? Because, I mean, we really, the image you get is after the reconstruction from the visibility. So another way to actually constrain the size of the black hole shadow is to actually fit models to the data, to the visibilities, not to the images. So we wanted to do this as well as to the images. And these are the fitting to the actual data. And we were using different Markov chain Monte Carlo nested sampler algorithm, genetic algorithm, and you can see beautiful paper sticks with all these details. And these are the results we obtained. This is for general crescent model parameters, the crescent models that we used before. So we know this model, we can compute the expected visibilities from this model, and we compare this with the actual data. And these are the values we obtained for the expected ring diameter. And you can see here, for the different fitting algorithm and for the different days, actually we got high and low band data for each one of the days, and you can see here the recovery sizes of the ring diameter. We also fitted the fractional width, what is the size of the ring, and we also fitted here what is let me try to see this because I remember. Yes, this is the relative the fraction of the flux between the central, the depression, the event horizon, and the ring. This is a measure of how dim is the central part as compared to the ring. And you can see here it's more than a factor of 10. And we did also the fitting with the actual images. These are the images, and we use a similar fitting algorithm to determine what is the expected ring diameter. And you can see here that we have really good, similarities between the different fitting algorithms and the different days. All of them showing around 42 microarcseconds in size. But we had to calibrate this as well, because these are the simulations, as you can see here. What we are really trying to measure is this lens ring diameter. This is determined just by the size of the black hole. But the emission may not come only from this. The emission may come only also from some of the accretion disk. So we had to calibrate our actual fitting of the data. And for this, we used the actual GRMED simulation because we knew the answer for this. So we knew that the size should be just this, the proportional to the mass and to the ratio between the mass and the distance. This is the ring diameter. So we had to calibrate these parameters, this alpha. How much of the emission we are seeing is coming just from the lens ring or some emission from the disk. As I mentioned before, we know the answer for GRMHD. So we did that. We did when we were calibrating our pipelines for the imaging. We calibrated with these our numerical simulations, and this is the values we got. And for instance, these are the theoretical values that we should get. Depending on the spin of the black hole. We know that should be around these values depending on the ring. By the way, in a few years we will be able to hopefully to get high angular resolution, better images, and just by measuring this alpha in the actual images, we will be able to determine whether we have what is the spin of the central black hole. Okay, and this is a summary of paper 6. The summary of the values we got. So these are the geometrical models. You can see around 3.7, 3.8. These are the GRMHD models, 3.8. These are, sorry, this is confused. This is the imaging, and this is from the image, the same 3.8. So again, we have done this again and again and again and again. We have done it in the visibilities, we have done in the images, we have done using a crescent model, we have been doing this in GRMHD model, so 250 pages to make sure that this is the actual number, the 3.8. And this is this is how we determine the mass of the black hole. These are the different values we obtain. So we know this, and then we can obtain m just using the distance. We have a pretty good estimate of the distance, about 16.8 megaparsecs, and with this we determine the mass of the black hole, and these are the 6.5 billion solar masses. This is a direct measurement from the image we obtain. Do these agree with the estimations we obtained before? This is actually in really excellent agreement with the stellar mass motion, with the stellar motions in M87 measured before. This is the estimate we knew before from the stellar motions, and this is from the gas. As I mentioned before, we had two different measures, and our measurements agrees very well. So just by taking a look at the image, just by analyzing our data, we we know that this should be a 6.5 billion black holes as it was determined before. So this is the main result from the paper, which tell us that we are really seeing a curved black hole in M87. And then we can have some tests of GR. We can have the null hypothesis is that indeed, this is the stellar mass, stellar dynamics, the gas dynamics, and our measurement agrees really strikingly, remarkably well with the stellar mass black hole. So this means that all results are completely consistent with general relativity, with the data we have now. So this is the first null hypothesis test of GR with an actual image of a black hole. And this is just for Carlos and for and Victor. So what do you think? I mean, do you think it's an actual black hole, maybe a boson star, maybe a GABA star? So we have a note at the end of paper 6 discussing a little bit this, because there are some black hole mimickers like boson star, GABA star, and so on. They produce different results. For instance, some of them may have a very difficult. It will be very difficult for these cases to produce the data that we have seen, and for also for other sources. That may mimic other objects that may mimic a black hole, you may expect that if they have a surface, and indeed they have a surface, you may expect a bump in the near-infrared emission. And the fact that the data from the EHT agrees with not having this bump in the near-infrared means that this object does not have a surface. It means that it is most probably an horizon, the event horizon of the black hole that is also capturing all the photons in the center and producing this drop in the emission in the center. And also the other test is the circularity. As you know, the shape of the black hole shadow depends also on GR and depends on the black hole spin. So we did a full analysis of what is the circularity, and we found that the actual ratio is smaller than 4/3. So this is really circular. It is quite truly amazing that we got this circular ring, because if you see the simulations, I mean, the easiest thing to have is to have something like a potato. And it's very difficult to actually produce a regular, very, very circular image of the black hole. And we did that. And this is in agreement also with the GR. Of course, this is something that with future observations we want to test further. Oops, sorry. Okay, I will show you now. Okay, many people have asked me, what happened with I-30A? So this is something that actually was posted in Twitter. So indeed, I mean, we did not forget you. I mean, we still love you, I-30A. And this is, of course, in the future. Okay, so let me just summarize a little bit. And probably the best way to summarize is just, that an image is worth 1,000 words. In this case, I think this is really true. And just to summarize, we do have this first picture of the black hole, and it is an actual picture. Some reporters are asking me, you got data, you did some wave things and so on. I mean, if you have taken a tag, I hope you didn't, but the same technique. We are using interferometry, and we got the very first image of a black hole. The shape, the size, everything is consistent. We have made this null hypothesis test of GR, and of course, this is just the beginning. This is the first image. We are adding more antennas. Of course, we did not forget I-30A, and we are doing polarization. Polarization is going to be really key to determine the accretion mode. As I mentioned before, we think it's a matter, it's a magnetically arrested disk. But with the polarization from M87 that we are analyzing now, we expect that before the end of the year, we will show you the polarization images from this to actually determine what is the accretion mode. And we are adding new antennas. We are adding antennas. NOEMA is going to participate in 2020. KITPIC is also participating. GLT is participating. We are going to have even more antennas than regular centimeter VLBI observations. So, of course, this is just the beginning. We expect to refine our images We are doing observations at even shorter wavelengths, so we are going to improve the angular resolution of our images. And of course, the main aim of the EHT is to have an image that could put GR to a test in a situation in which it has not been tested before, really, really close to the event horizon. So I'll leave it here. Thank you very much.
Thank you, Jose Luis, for this very nice talk. And I need to say that this is the first time that I see a full hall for the seminar. So now it's open to questions.
I have a very simple question. Are you going to take more data on this galaxy, on this hole, or are you going to do a survey or looking for another holes?
Excellent question, Luisa. We are taking more data on M87. We did another set of observations in 2018. The weather was not very good in 2018, but we did observe M87 Sagittarius A. The two main targets, and of course, I mean, we are going to observe in 2020 and so on. These are the two main targets, and these are the main targets because they have the largest apparent size of the black hole. At least for all these measurements of the black hole masses that we have so far in nearby AGNs, if the estimation of the black hole masses in those sources are real, are good estimations, I mean, they are going not to be possible to be observed with the HT with the angular resolution of 20 microarcseconds. But we will be able to keep observing the, I mean, M87. If you think about this, why are we so excited also about this? Think about LIGO. LIGO observes what just a flash or whatever it observes, and observe the dynamics of the space-time. It's just a chance of observations. You cannot repeat the observations. M87 is not going away. It's not going to be away anytime soon. So this is a source that is going to be there for the rest of our lives, and we are going to take as many pictures as we want. And this is an amazing laboratory for science. It's difficult to find such a source like this, and to have such an amazing opportunity to refine our imaging and to provide this further test to GR. So M87 is definitely going to be a star in the next decade. And in Sagittarius A, of course, even the black hole size in Sagittarius A is even larger. It's about 50 microarcseconds. But it's been difficult to image M87. And in the Black Hole Initiative, in the meeting we had in July, we actually looked at M87. Katie did the comparison, and it was lousy. So we had 4 different images for the 4 different teams, and they did not agree. So we did not proceed further because we know that there are some problems that we still need to solve. There are 2 main problems. One is the scattering in the galactic center. This is blurring our images. It's going to be very difficult. And the other issue is that Sagittarius A is a much smaller black hole. It's 1,000 times smaller than M87. So the variability scale is about 10 minutes. The whole idea, the whole thing about the VLBI and so on is based on the aperture synthesis for which Martin Wright got the Nobel Prize in 1974, which is that the Earth's rotation is going to cover to fill your UV coverage. But this is based on the assumption that during the UV coverage, the source is not changing at all. But the Sagittarius A is changing in a time scale of 10 minutes. It's like you are taking a picture. I mentioned this to reporters. I mean, immediately you are taking a picture in a situation like this, low light and so on. If your exposure time is 2 minutes, the image is completely rubbish. It's completely blurred. And this is the very same situation we are facing with Sagittarius A. So most probably what you will see, hopefully by the end of the year, if we manage to solve all these issues, is a movie of Sagittarius A instead of a picture.
Well, congratulations to the team for such a complex effort during so many years, and to you for your enthusiasm during these hectic days in spreading us all the results. Could you show the image for the 4 different days, consecutive days, the results? And the question is, if I'm not very wrong, these 20 microarcseconds are roughly 2 days. So do you you can see clear difference between the two left and the two right images. Do you think this would be real?
This is actually the case, and we have been discussing this in paper 4. I mean, if you go paper 4, at the end we have noticed that there seems to be some small changes between the 2 first days and the last 2 days of observations, but this is not something that we can actually pinpoint now. I mean, we have seen changes in the visibilities between these days, so we know that there are some changes in the source. By the way, we expect changes in M87 in a time scale of about 3 weeks. In 3 weeks, we should have seen real, measurable changes. But these are just, 6 days, and there is some hint of variability. But I mean, with the current data we have so far, we cannot tell precisely where these changes are coming from.
The second question, you show us the rate of increased exponential rate of increasing of data recording.
Yes.
It is the main reason why this experiment could be 2 years ago or finally?
Absolutely, you're absolutely right. Enrique, I mean, this is, you can see the rise here, these are 32 gigabits per second. I mean, to give you an idea, this is a regular centimeter VLBI. This is what everybody uses. This is what has been used for decades, and now VLBI, which is the best one, does 2 gigabits per second if you ask and you have a very good scientific case, and you get 2. And we are having 32. And this was 2017. For 2018 we have 64. So this has been really instrumental. Without this, we could not have obtained this data set, these high signal to noise visibilities that actually are so robust that produce these very robust images and analysis. In the observatories, especially IRAM, I mean, Pablo, Miguel, they have been, I mean, all these, I mean, they spend, days and days hoping, the weather is good, staying there, keeping a good track of all the data sets. I mean, of course, with all these people, I mean, this wouldn't have been possible. I cannot stress this more. I mean, this is not, I think it's probably the best example of collaboration. To my knowledge, I haven't seen, such a amazing collaboration in which the results were advertised in press releases around the globe, and the reason is because really this cannot be done by a person of a single instrument. This is the best example of collaboration we could have.
Okay, Alex. No, first Pepa, then the.
Thank you, Jose Luis, for this really good finding. I am very happy. Well, first I want to make a comment, because when I understood that we were going to see the black hole in M87, that, as you know, is a liner, because I am interested in these low luminosity AGNs, I was really happy for those that discuss the AGN nature of liners. So definitely nobody will discuss in the future about this kind of thing, at least for M87. I have also 2 questions that I thought yesterday when the announcement came. Is nobody tried to do this in the microquasar in our galaxy?
Keep in mind that this is 6.5 billion solar masses, and the size of the black hole shadow is proportional to the mass of the central black hole. So we are talking about 6.5 billion times bigger than any microquasar in our galaxy. So you need a 6.5 billion times better angular solution to see something like this in a microquasar. I'm afraid I'm not going to see that. I don't know you guys, but I mean, this is really out of the reach in the next decade. So, I mean, even with space VLBI, it's not going to be possible.
The other question is about the field of view you are looking at. You can reproduce is only that field of view you show us. Yes. Yesterday also I was wondering about the jet of and the connection between. I suppose the material you are looking at is synchrotron emission in the central region of the accretion disk. And as far as I understood, the jet is coming from the central part of the accretion disk, and I wonder why I don't see any trace of the jet. So that's all.
Months with this question, Pepa, and the key point is the UV coverage that we have. Let me show you. Yeah, look at this. You see this hole here in the UV coverage. This is because the shorted baseline we have here is too large to actually image the jet. We don't have information about this, and these baselines are the baselines that tell us where the jet is. So what we did is, we don't know this, so we just put a very big Gaussian to account for all these flux. But we didn't even try to image this because it's not constrained by our data. And to image this, which is, truly, I'm very particularly interested in that as well as Anchon, because this has been all field for decades. We want to see how the jet actually is emerging from the central black hole. That would be like a dream come true, to actually see it for the very first time. But for this, we do need these short baselines. But nevertheless, in 2020, we are adding NOEMA and KIT-PEAK. NOEMA and KIT-PEAK are going to fill the gaps here. So we hope that in, say, 2 or 3 years, we may have the first image of the black hole and the jet emanating from the black hole. And hopefully even a movie of the black hole and the jet, how it's being produced and collimated and launched and everything.
Do you have an estimate of the flux density of your source? You have a very high resolution, so obviously you're only seeing a very small part of the complete Virgo A source.
Spend a lot of time on this, and this is and if you can see here, and if you go to paper 4, we have a full section on what is the expected compact flux that we could get. Because as Pepa was mentioning, we expected some flux from the jet, and we know there is a jet, and we know that some of this flux is from the jet, and we think it is about half of the flux is in the jet that we cannot image. So one of the parameters we have been testing in all of different pipelines is the compact flux in DFMAP, EHT imaging, and SMILE. So we have been using the synthetic data set that I mentioned before, in which we knew the ground truth value of the compact flux that we are imaging in the ring, and we trained our script to capture that, and we used those parameters to image M87. And this is the best estimates we obtain is that the flux that we see in the ring is about half. It's about half a Jansky, which is about half of the total flux that we see with just a single dish of observations of M87. But this is truly a key aspect also of the imaging.
Yeah, well, I was planning to ask you something concerning the jet as well, but Pepa already did, so that's okay. And I had a comment, so I'd like to make a comment, which in fact is just to congratulate the whole team and you in particular. And I take profit to congratulate, to include our institute as the object of these congratulations, but in fact I would like to extend it to astronomers in general, because I think that in this global world we are living today now, it's just to show to all people that non-profit science is able to put together a whole team of great people making things with non-profit and non-commercial activity. And I think that all the fields of science should take that into account in order to take the lesson that big results can be obtained when all researchers are working together. So my congratulations.
Thank you very much. I think this is point. I mean, you could not believe. I mean, almost all the reporters have been asking me. I mean, what is it useful for? I mean, one day. VLBI, no? You know, and then I had to find. And, you know, do you use GPS? Oh, yeah, of course I use GPS. You know that without general relativity you could not use a GPS. I didn't know that. You know, this kind of things. I mean, you think that Albert Einstein was thinking about GPS when he was developing his general theory? So these kind of questions. And also I like to stress your comment, Isa, that I mean, the welcoming that we had in CSIC, and Sean can speak for ourselves as well, the welcoming we had in the CSIC for the presentation was truly amazing. I never seen people so inspired, so eager to see this. I mean, the president of the CSIC, I mean, Rosa was really extremely kind, extremely happy, Rafa and everyone. I mean, they have not had any like what we had on Wednesday in the CSIC. I mean, that was the biggest presentation that the CSIC had ever, and they were really very happy. And the minister that was talking to Rafa and mentioned that this has been a truly successful thing and very inspiring for everyone. And I suggest you to take the opportunity. I mean, we are now in the eyes of the CSIC. I mean, let's take this opportunity. We are now at Severo Ochoa. We have made these headlines. IAA is on the headlines everywhere. So use these. You know, if you intended to ask for, you know, 1 million, ask for 2. Let's give it a try. Let's give it a try. And it's a wonderful opportunity that we should try to.
Okay, since Jose Luis is here, well, first thing, let me congratulate you for your talk. I have to leave. And the reason I had to leave is that we got a phone call from the president of the Junta Andalucía just now, from Juan Manuel, just now. He was phoning, just congratulating the Institute for this result, you, the team, and the Institute for this result. That's IAA. In that sense, I think it's very positive. Second thing, as he will be visiting the Institute next June, he promised to do it. In fact, I told him, I thank him because the incorporation of the Junta Andalucía to Calaralto, also that was just one day before. And okay, in that sense, I extended to you just now, yes, in streaming, okay? and two things before I finish. Probably you said that, I don't know. I mean, you know that the results of this research have been published in 6 papers in Astrophysical Journal. Can you give just the basic details of each of one of them, and then people can take the one that is more interested?
Of course. Special number of Astrophysical Journal. I mean, as I mentioned before, there are about 250 pages of papers. Paper 1 is a summary of the whole thing. It's a beautiful paper. I mean, it took us, you know, I mean, telecoms at 1 a.m., which you have to go with a helmet, you know, because you have here Shep, you have the Heino Falke, you know, the people that may get a Nobel Prize and fighting with you and the rest of the people. So you really have to wear a helmet. And, you know, it has been evolving a lot, that paper. And at the end, it has been a beautiful paper. I mean, please read it. If you don't want to read 250 pages, please read paper 1. It's a beautiful paper that summarizes all the really hard work. I mean, I don't remember, I mean, when I go home, I mean, the kids say, who are you? I mean, it's like, really, I mean, it's been weekends, it's been telecoms at late night, it's been hundreds of emails every day. Very pushy people, you know, doing the hard work. And as Michael mentioned before in an email that he sent me this morning, I mean, we are all really, you know, amazed by the capability that we can push each other. And this, you know, having this clear goal is amazing, because when you're writing a paper, you know, it's a good paper in the map, but this was, you know, we knew that there was headlines everywhere. So this is a very powerful, you know, and we were pushing each other, you know, and so on. And we managed to write this in 2 months. The 6 papers are written in 2.5 months. And we managed to do that after 2 years of data and so on. So it's been truly an amazing experience. And
okay, yeah. Paper 2 is a description of the array. Paper 3, okay. But I agree with him. Please read paper 1, and you choose the other one that you want to read.
Paper 2 is the explanation of the array. It explains the EHT. It explains how we managed to put all the this there. You know, And paper 3 is the data calibration. It's just, the 3 different pipeline, Hobbs, CASA, APES, all the amazingly detailed analysis. You cannot believe this. This has never been done in VLBI. Paper 4, please read that one. Please read that one. This is my paper. I mean, this is a beautiful paper, really, truly amazing paper. Beautiful. Paper 5 for people interested in GRMHD. Beautiful paper about GRMHD simulations. And paper 6 is the fitting of the whole thing and the final number of the black hole mass and the agreement with general relativity. So 6 really, truly amazing papers.
And just to finish, as a personal question, how do you feel sharing the secret after a year, keeping it and closing your...
Shep was sending an email every day.
Yeah.
Every day. When you are being asked by the reporters, please say, contact my PR representative and so on. This was going on every day, every day. You cannot imagine 50 institutions without their own PR and everything. So the chance that this was being, leakage was very high. And as I think I mentioned to you personally, to some of you, I mean, this is not like LIGO. LIGO is a plot that you have to know what you are seeing. But other than that, I mean, it's just a plot. But this is the image. And it could be just 20 kilobytes. I mean, it can be just go everywhere. So the last risk was like, oh my God, I hope I don't see the image. I could not talk to any one of you guys. I mean, and as I mentioned before, 9 months. My kids couldn't tell to anyone. They knew because they saw me, at night in my bed making images. And friends would come home and they would not talk to anyone. So it's been a nightmare, absolutely a nightmare. So on Wednesday, I was like, finally, here's the image. Okay, you can tell the world. Finally.
Then, sorry. Now we are going to congratulate Jose Luis, but first I ask you to stay here just 2 seconds after congratulating him, okay? But please stay here. Yeah. Okay. Yeah, just some few words, just sharing also the Products Institute. I want just to mention that that our colleagues of the space research here in the Institute got el Premio Granada de Ciudad de la Ciencia last week. Then I want to congratulate them, and in fact just mention that the same Wednesday, our press release was at 3, the same Wednesday at 7 p.m. the first results from NOMAD and ExoMars were coming with no detection of methane, etc., but with a lot of work there. I mean, work from the instrumental point of view and both from the scientific point of view. Congratulations to all of them also. Okay, that's all.